Yes, here we are once again. It's the Physics 2A video lecture. Physics 2A video lecture 16. And our topics today are oscillations, resonance, and waves. So this will wrap up that chapter. I also have a bunch of demonstrations for us in the oscillation section. I had intended to just go straight to waves, but then I realized there's just too much to talk about. So let me show you a few interesting things about oscillations. And then I'll have to remember to give you a heads up on a good resonance video that you guys can find online. But good, we're going to start with the oscillations. And we had ended by talking about pendula. And here I have two connected pendula. Now let's see, let's turn them this way. Connected by a spring. So the progression on this discussion here is as follows. I'm going to take the spring off, and now I just have two identical pendula. So I can have one swing here and another one, and they have the same period. Maybe the best way to show that is to just let go of them simultaneously. So they're oscillating towards each other, and you can see they have the same period. Okay. And this is a pretty close approximation to the simple pendulum we talked about the other day, because most of the mass is concentrated here and not in the rod. Good, so they're the same frequency. Now I'm going to connect them with a spring. We have three places on this device to connect them. The spring in the middle is pretty ideal for showing the effect that we're looking for. Okay, the spring is pretty much massless, so I can pull them both to one side and let go, and then it's as though nothing had changed. Okay, if I pull them both to one side and let go, they're just swinging with the same frequency, same period that they had before. Okay. Now, if I pull them apart and activate the spring, then it's going to pull and push. Pull and push. It's going to add a little bit of force, and the frequency is going to be a little bit higher. Okay, simply because it's going to add a little bit of extra torque to the equation. The inertia has stayed the same. The torque's going to increase a bit. Yeah, so here's the effect I want to show. I'm going to pull one to the side and release it. Okay, now I'm going to release them simultaneously, and we're just going to see an effect that may be unexpected for you guys. Okay, marks, get set, go. Okay, so what we notice is that the spring is acting on the other pendulum, and now they're both swinging. What we may not have expected is that this one is going to come to a dead stop right now, and this one has all the energy. The energy has been transferred from one pendulum to the other, and this is going to repeat itself. So now we see this one slowing down, and some instant, pretty soon it'll come to a dead stop right now. Okay, right there. And this one is swinging fully. And so this will go back and forth for as long as the small amount of friction doesn't cause the oscillations to just decay away. So we can have this back and forth a few times. So these are referred to as coupled oscillations. And the phenomenon we just saw is referred to as beats. So you could say there is the frequency of these pendula that we already knew about, but then this slower motion that's going, the back and forth motion, is called the beat phenomenon. Okay, so that doesn't get much better than that. That's a real crowd pleaser there. Kids love it. Okay, so that is the phenomenon of coupled oscillations and beats, and let me write a couple of things down now. So our demonstration, coupled oscillations, and what we have here, just for the record, is a pendulum, mass, and L, another one, mass, and the same L, right, suspended from this frame here, and a light spring. You don't want, right, you notice this is a very soft spring. Okay, suspended by spring, and we just saw what happens. These can oscillate, these can oscillate. I'll say that there's a theta sub 1 here, and there's an angle theta sub 2. Now I'm going to give you a graph of what we just saw, and let's get this out of the way. Give you a graph of what we just saw in terms of the angle as a function of time. Okay, we talked about the pendulum. We know that, in fact, let's go ahead and remind ourselves the period of the pendulum, 2 pi root L over M. Okay, so those were the two original periods. Now, what I want to draw is on top of each other. Let's straighten up, yeah. Graphs theta as a function of t. So this will be theta 1, and directly on top of it, leave yourself some room for this graph. This is a great one. This will be theta 2 as a function of t. Okay. And the angle, let's see here. Theta is equal to theta 0 cosine omega t, basically. And you know, we have the omega is the square root of g over L. So, and that's a g there. Just so that we have everything up here on the board, all the technical stuff. Good luck with that g there, okay. G over L. Yeah, so we want these graphs of what we just saw happening, and here I'll even put generally theta of t right, it's a cosine. So what we just saw was that cosine, but modified in a certain way. What I'm going to do is use a different color and draw out a dotted line here. There's our cosine, and we can continue it like that. First I'll draw, then I'll explain. 1, 2. Okay. That's a little too long here. Okay. There we go. Okay, so what were we looking at? The theta sub 1, which was that one of those oscillators, the one I let go of first, it was oscillating like a normal oscillator, but its oscillations got smaller. So this was the point at which I said it came to a dead stop. And then let's look at what theta sub 2 is doing at the same time. Okay. Theta sub 2 so what I'm drawing is the envelope there. So theta sub 2, as theta sub 1 was oscillating, this one was at rest at first, but it gradually started oscillating and getting a larger and larger oscillation until when this one was 0, put this right there, when this one was 0, this one was maximum. And then it goes back and forth. So this one was 0, then it started oscillating again. Kind of a neat graph, you gotta admit. And then this one was maximum and it started decreasing again. And then its minimum lined up with the maximum up here, and back and forth. So that's called beats. So let's call this coupled oscillations beats. And so you'd ask, what is the period of the beats? Well, you can see it here. Let me continue the red one up here. You can draw these as much as you want now that you see the idea. So the original period is just this very small amount of time, okay, on my graph. But the beat frequency and the beat period are this larger one here. So let's go ahead and just do a peak to peak. There is our beat frequency or beat period. And the closer together these frequencies were, the greater that beat frequency will be. Okay, I'm not going to give you the formulas. It's basically the difference of the two original frequencies of the device gives us the beat frequency. There we go. Now, where else does this have applications? I'm going to give you a couple, mainly two. Now, this demonstration I had out the other day, I'm going to explain it a little more. What it has is a vertical mode, okay, up and down, the pendulum on the mass on the spring. You guys had that in your lab, But it also has a torsional mode, so I can just twist the heck out of this spring and let go, and it's got a torsional motion. Okay. So there are two frequencies, the up and down frequency and the back and forth twisting frequency. And with this device, it's been tuned by these little bolts on the end here. You know, if you move these bolts, these nuts out or in, the moment of inertia changes and the twisting frequency changes. So here's what I'm going to do. I'm going to twist this thing up in a major way and just release it and see what the camera catches. It starts out with a purely twisting motion. Let's do once more with feeling here. Okay, so it starts out with a purely twisting motion. It'll let go properly here. And as the twisting motion subsides, it converts to a vertical motion. Now, I don't know if the camera will catch it, but at some point the twisting will completely cease about there, and then it's going to start twisting again. And as it starts twisting more, the up and down motion ceases, and it's now just a purely twisting motion about there. Okay, perfect, right there. It's only twisting, and now it's going to go back into the vertical mode. And that's also a version of this type of motion right here. Coupled oscillations and the beats. Okay, I'll call that a success. Now there's another aspect of this, and we're not really doing the chapter on sound, but I did bring a couple of nice sounding objects here. Okay. So we'll have to see how this comes through on the video. Okay. And then now, nice tone, right? So about the same, if I hit this one, we're going to get what's called resonance, and this one will actually start sounding a little bit. Let's go ahead and hit this one. Still have a faint sound right there. So that one is actually picking up. That's already an example of resonance, but I'm still actually trying to talk about the beats here. If I hit these both at the same time, there's a noticeable change in the volume somehow. Let's see what we'll call this. So you hear the sound fade in and out slightly. Possibly, if I attach this little clip here, I can change the frequency a little bit more and make that a little bit more pronounced. Let's give it another try. Yes, okay. So what's happened is I've made these frequencies slightly different, and what we're getting is that in and out of the sound, slightly louder, quieter, is essentially the beat frequency, or is the beat phenomenon that we visualized here graphically. Okay, so the red lines would be the normal frequency that you're hearing, and the slight in and out is the coupling of the oscillation, so that would be the blue, the envelope there. Okay, so yeah, a lot of stuff. This is just the beginning. Yeah, we'll see how it comes through on the video later. Okay, good. Here's your chapter on sound. Okay. So we have oscillations. Now I'm going to talk a bit about resonance. Bring this one off stage. So now we're back to this device that we had the other day. And now what I want to talk about is the natural frequency of each of these. These are just metal spokes. We got the same ball on top of each one. And you can count out the period or the frequency. 1, 2, 3, 4. Okay. This one here is going to be a little more rapid. 1, 2, 3, 4, 5, 6. Okay. And this one here, I'm not going to bother trying, but you can see it's much more rapid. So each of these has what we call its natural frequency. Now what I can do is drive this oscillator by grabbing this handle and pushing the board back and forth. Okay. So if I drive this oscillator with a slow frequency, in fact, if you count, you'd see I'm barely driving it at all, but I'm driving it with the natural frequency. I'm driving it with the natural frequency of this oscillator right here. And what's happening is the other two are essentially not involved, they're not moving. So this one's responding to its natural frequency, and that's called resonance. So that's the resonance phenomenon right there. Just so I said it, just so I wrote it down. Resonance, when you drive an oscillator with its natural frequency. Now here's the interesting thing. This is, by the way, the all-time demo. Dr. Hall brought it in here years ago. It's the all-time resonance demo. So what I'm going to do is just drive this board here with that frequency, and we can get the middle one to move and the other two not. Okay, so it's just responding to its natural frequency. The other two are getting nothing out of this. Okay. Okay, and if I had some strong student here, I would ask him to come up here and drive this one with its natural frequency, because then you got to really lean into this. Okay, I'll spare us that. I think the middle one's really the impressive one, because it's framed by the other two that are basically not moving at all. So there are many examples of resonance and systems with natural frequencies. So let's add the concept resonance and natural frequency. In terms of what we've been doing, this was the natural frequency of a pendulum. Okay, so it's nothing fancy there. So resonance and natural frequency. Many systems have a natural frequency. A rocking chair, the water in a basin has a natural frequency, and if you drive a system with its natural frequency, you can get what's called not only resonance, but a resonance catastrophe. Because I'm not driving this thing hard, but you can see the tall spoke is just going to town, starting to smack the other ones. So there's also the concept of a resonance catastrophe. And you know, I'll erase some of this here so we can have some room to put these new terms down. Because I don't want to forget the heads up on the resonance catastrophe. So we have driven oscillations, just giving you some good terminology. We have resonance, and I'll even put here the resonance catastrophe. Okay, resonance catastrophe. Now this one here, you can look up at a very famous resonance catastrophe in which an entire bridge, and I don't mean a little one, a big one spanning thousands of feet, was shaken to death in some way. You have to look it up. You have to look it up. Resonance catastrophe, it's called the Tacoma Narrows. Tacoma Narrows. All you have to do is do a search for Tacoma Narrows and find some good video footage on it. This happened in the early 1940s, I believe. So the Tacoma Narrows catastrophe, I couldn't describe it if I wanted to, okay? You gotta have a look at it. This gigantic suspension bridge is just twisting and buckling and finally breaks apart. One of the all-time great catastrophes. Okay, nobody was hurt. Now, so we're talking about resonance, and we have the resonance of the driven oscillations. I just wanted to give a couple more examples for you where you can experience this. One place is if you've ever carried, say, soup in a bowl across the room and you're worried about spilling it. Okay, the reason it sloshes over the plate or the bowl is because your frequency of steps that you're taking is the same as the frequency of sloshing. Okay, so waiters and waitresses know this. They have to actually break their take steps at a different frequency in order to avoid that. Yeah, try that out as a demonstration. Carry a bowl of water across a room, or a plate, soup bowl, and see the difference. And there are many others. There are infinitely many examples of that. So we're going to have to move on. So let's see, we talked about oscillations and resonance, and now we're finally going to talk about waves. See how many minutes we've used. Trying to limit this. Okay. Waves. This is the last part of our chapter. And I can erase everything and start with a couple of demonstrations on waves as well. And waves are very related to oscillations, tied in with oscillations. So you have to talk about both of them, and we are. So we're now going to discuss waves. And what I'll do is give a demonstration. First of all, very simple one. This is a plastic slinky. And all that I'm going to show is that I can send a pulse across, and you can see this pulse quite clearly. It is a pulse. And this pulse constitutes a wave. So the definition that we're looking at is the following. The wave propagates through a medium. In this case, the medium is these plastic coils. Propagates through a medium, but there's no actual transport of mass. Rather, there's a disturbance that propagates through the medium. So we've got, for the wave, a disturbance. I'll put that in scare quotes for lack of a better word right now. Propagates through a medium. not transporting a bunch of mass, but it was clear to see. Now, we will find, in fact, next semester you'll learn that electromagnetic waves propagate through the vacuum, but we're not there yet. Okay, light waves, electromagnetic waves. So we're just going to learn the understanding of waves that propagate through a medium, and our examples are going to be, well, first of all, the slinky, since there it is, the slinky wave. And next thing I'm going to demonstrate is the rubber band. Now I notice this doesn't really show up so well on the video, but we're going to give it a try anyway. So this is just a strong rubber tubing here. And what I do is I pluck it and the pulse propagates back and forth. Okay. And that pulse, I checked it out a minute ago. It wasn't really showing up that much, but I'm going to try this anyway. So if I pluck it, stretch it more, the pulse is more rapid. What may show up better for you guys is if I take this and have it less stretched out, and you possibly see that pulse. It's not the up and down motion. What we're trying to find or view is the pulse. Pulse propagating back and forth. Okay, so that's the rubber band wave. And other examples then, water waves. Okay, and then there are sound waves. So there are different types of waves. And in all of these cases, nothing's being transported through the medium except for the disturbance. Okay, so if I pluck the rubber band at this end, over at the other end, there's a little smack. Okay, and here you can see the pulse go across there. I could even do two pulses, and they looks like they're bouncing off each other in the middle. Okay, so that is our beginning discussion. And in fact, I should even add this: the stadium wave. The famous stadium wave also fulfills this criterion right here. Let's go ahead and put that down as well. Stadium wave. Okay, now I have to get a little more technical. So we'll erase these definitions and look at a water wave. I'll draw a water wave. Namely, the disturbance on the surface of water does something like this. And if you've ever been to the ocean, let's go ahead and erase these. If you've ever been to the ocean out behind the breakers, and waves come in, swells come in, you'll just be bobbing up and down. They pass under you, and then they move forwards towards the shore, okay? So there's your water wave. And I'll go ahead and do this. We can see that there's going to be a wavelength here. And I'm going to call the wavelength lambda. That's the traditional letter for the wavelength. And it will go from here, there's the peak, there's the trough. So there's our wavelength. Okay, that's the wavelength lambda. Now, like I said, if you're in here floating, why not? A little stick figure. Okay, you're floating and this wave is passing by, and say there's a whole train of them, then you're bobbing up and down. And you'd be bobbing up and down with a frequency, okay? So wavelength lambda, frequency f. And we talked about frequency before, it would be in hertz, number per second. So how about this? Lambda equals meters. Frequency f equals 1/seconds equals hertz. And a relation that holds true here is that, so this is about a water wave. Let's go ahead and put a little arrow here and say direction of propagation. So that's the other thing, direction of propagation. And then there's also a speed, maybe I'll put a little v here. The other relation I wanted to get to now is the speed of the wave is lambda times f. Happens to be the speed of propagation. And then we've got the speed of propagation. Lambda times f, what are the units of this? Meters per second? Meters times 1/seconds, meters per second, okay? So that's the fundamental relation between wavelength and frequency when you have wave phenomena. Okay, now I haven't shown you this kind of wave yet, but I have one more demo for us. This is a wave machine. One of our all-time great demos here. Okay, I'm gonna put it right here. And the description of this thing is that there is a wire here along the spine under the ruler there, and that wire twists back and forth. These rods here give it more inertia, and they'll demonstrate its twisting motion. So if I just give this a little burst, you can see a wave propagate over there. And that kind of reminds us of our water waves there, okay? I'm gonna have to introduce some more terminology. I'll say it now. It's called a transverse wave when the motion of the agitated motion, is perpendicular to the direction of propagation, okay? The direction of propagation is along this direction here. The motion of the rods is up and down. So there you have it. That's worth the price of admission alone right there. Okay. Now there's more to be seen. You notice this is a driven oscillation because I'm driving it right here. And so if I drive it with a slow frequency, you'll notice I get a very large wavelength. Okay. The slower the frequency, the larger the wavelength. Okay, let's see if we can quiet this thing down. Good luck. There we go. Now I'm going to drive it with a higher frequency. I'll count them out, 1, 2, 3. And you can see I'm getting a shorter wavelength. Okay, so higher frequency, shorter wavelength. Okay. And the speed in both cases is the same, or in all cases is the same. So for our device right there, we have this wave speed that's given, and then if I have a higher frequency, I have a lower or smaller wavelength, and if I have a smaller frequency, I have a larger wavelength. Okay, so it's that inverse relation right there. Okay, this wave machine is pretty good. There's one more thing I can do if I apply a little skill. It's called a standing wave. If I get this with the right frequency, the pattern is stationary. A little difficult to do right now. Okay, we'll declare victory on that. Okay, so now that terminology I had promised you, and then we'll move on. So what we have is transverse waves. And for the transverse waves, the motion in the medium is perpendicular to the direction of propagation, okay? Transverse waves, motion is perpendicular to the direction of propagation. Fill in those little words there. Motion perpendicular to the direction of propagation. That's a transverse wave. Now this wave was different. There the motion was parallel to the direction of propagation. In fact, this pulse that I'm sending is really just a little compression that is pushing its way through there. That's called a longitudinal wave. So a transverse wave, and we have a longitudinal wave. Good to have heard about. So the transverse waves are, for example, the water waves, the waves on our nice wave machine there. Those are the transverse waves. The longitudinal waves are the slinky, which isn't that important in physics, right? But sound waves, sound in a medium, sound in air, sound in water, sound in a solid. Sound waves are also longitudinal, so they're very important. Okay, the last thing I'm going to do today is talk about the waves on a string where I can actually derive an important relation. And then I'll give about a half a dozen interesting homework problems that primarily refer to these waves on the string that I'm about to do. So yeah, let's see how much time we've taken so far. Okay, now we're doing fine. I'll do another 10 minutes or so, and then we'll call it good. Now the waves on a string are interesting. For example, in music, you have vibrating strings, stringed instruments, and this formalism holds for them. Relations between frequency, wavelength, resonance in the body of the instrument, it's all being talked about right here. Okay, so waves on a string. The string can have some tension, and what I have to do is imagine the string is under tension, string tension T. Okay, so we're not going to confuse the letter T with the period here. It's going to be the tension again. We could also call it F. So we've got a string under tension T. Let me go ahead and, we've got a string here under tension, and maybe you've got a thing here where you can twist it tighter. But when you play that, pluck it, you get waves that propagate. Let's try that one again. Trying to just draw a nice wavy line here. You guys do one too. Okay, there we go. And you saw it on our wave machine, so it's believable. Now, this analysis here is great. So here's our string. Our string's in blue. Yeah, I could use different colors here. What we do is we look at a little section of the string here, and I could maybe exaggerate its curvature a bit. And we ask about the physics. What's going on with that string? We know that this pulse is propagating to the right and maybe bouncing back, coming back. So the force on this little section of string is due to the tension, and because it's curved like that, the tension is pointing down a bit. Now this string has a radius of curvature, so let's imagine that this is that section of a circle here, and we've got a little opening angle theta, and this circle is the radius of curvature r, and we have these tensions here. What I'm going to do is derive this formula that's in the book. They didn't give the derivation, but we love these derivations. Okay, yeah, so what's happening with the tension pointing slightly down? It's going to pull down on that string, and it escapes out to the right here, but the instantaneous effect is pulling down on it. So here's the interpretation of what's going on. We have that angle theta there, so I'll label this in red. We have theta over 2 on both sides, just by the geometry of this. So in the down direction, we have t sine of theta over 2 twice. So that is the force pushing down on this. And what we're going to interpret the force is, because this is kind of rolling through, as a centripetal force. Okay? So we're going to interpret it as mv squared over r. So yeah, let's say Fc equals mv squared over r. There's our Newton's law, and that's what we're saying for this little segment of string. Okay, so here goes. We're going to use a small angle, and theta is small. So the small angle approximation, sine theta over 2 is approximately just theta over 2. So on the left side here we have 2t theta over 2. On the right side, we have this mass. The mass of that little segment of string is equal to mu times r times theta. Let me explain that. That's mass per length times a length. R times theta is S, is a length. Okay, so mass per length times length, and then we have this v squared over r. So yeah, the simplification here is amazing. 2 cancels, r cancels, theta gone, and what are we left with? V squared is equal to the tension divided by mu. So I'm going to spend a little more time talking about this because that was a little fast. But what we've found is the formula for the speed on a string. So let me analyze it over here, left side of the board. So I'll put the formula down in its official form. We've got the tension divided by this letter mu, and mu is the mass per unit length. Okay, so if you have a thin string, you have a certain mass per unit length, and of course it's kilograms per meter in our world right here. So mu is kilograms per meter, and what it means is it's the mass per unit length. Okay, and then we've got the tension. And then we've got the speed here. So remember, so I'll just put here as a note, lambda f is equal to v. So now we can talk about the musicality of this situation. So given a certain wavelength times frequency equals v, the v can be found from this expression here. Let's first of all just talk about the v. If we increase the tension, the speed increases. Increase the tension, the speed increases. If we increase the weight, or the mass per unit length, then we're in the denominator, the speed decreases. So this is why a higher tension corresponds to a higher pitch. In a, say, if you have a musical instrument and you put more tension in the string, the pitch goes up, okay? Because what you're doing is increasing the speed here. The lambda is going to stay the same because that length of string that you have is staying the same. So you're increasing v, lambda staying the same, you're therefore increasing the frequency, which is the pitch. Okay? So a lot of good and interesting applications of this formula. It makes sense, and With my rubber band demo, I don't think the camera picked it up, but when I stretch the rubber band, I'm actually increasing T, of course, when I stretch it more, and I'm decreasing mu at the same time because I'm stretching it out. And in that case, the speed is much higher, and you can actually see it. I'm not sure if the camera caught that. Okay. Good, so this formula, very important. You've got the tension, so the mass per length, and I'm going to assign a bunch of problems that primarily deal with this formula in a number of interesting ways. Let's see what I have. I should actually consult this book before I put them on the board. I wrote a list of the problems I wanted you guys to do. Let's have a look here. So we're in chapter 13, vibrations and waves. Yeah, this is a really rich chapter, rich in phenomenology. Let's see what we have here. Yeah, right there in that section. Okay, so I'm just plug it in ones, piano string, transverse waves, so then, okay, then there's a problem that involves the pendulum, so these are good. These are all good, and in fact, any of these problems that I'm about to put on the board are reasonable exam type of problems. Nothing too difficult about them, a little bit of application. One of them, they hang a ball at the end of a pendulum, and then you can talk about the period of the pendulum, but because that ball provides tension, you can also talk about the speed of waves on this. So it's a nice combined problem. Good, let me write up right here what we have. So homework, this is our last set of problems, hope you love them. I just have all in the 50s here. So 51, 53, 55, and 56, and 57. Blow through that entire set here. This, of course, is chapter 13. Good, so enjoy these. These will be the last notes I'll want you to turn in, I'd say by Wednesday of the coming week. Not too uptight about that though. Just make sure you get them in during the week. In fact, yeah, let's just make this for Friday the way the other ones have been as well. Okay, you guys have plenty to do. So we'll have them all in by Friday. And as always, take really good notes, leave space. There's a whole lot to be learned right here. Good, see you guys next time.